Okay. So, yeah. Just 1 second. One more second. Fair enough. Now, so about capacitance, um, let's write. Let's first know what exactly is a capacitor. Okay. So capacitor is known as a solid state device. Solid state device that stores energy by redistributing charge. Okay, so this is the definition of a capacitor. Capacitor basically has a symbol like this, but in reality it looks like a cylinder, two bars like this. Okay, now so when you look at capacitance, capacitance is the ratio of charge on one of the plates to the potential difference across the plates. So usually this definition will come for 2 marks, one with respect to the charge and one with respect to the potential difference. So the symbol is C, and the formula for this is C equals to Q over V. It is a scalar quantity, and the SI units are coulomb per volts or farads. Now farad itself is a very big unit, so usually you find it in microfarad, millifarad, like that. Okay, small ones. Sometimes in picofarad as well. Okay. Now please write this down so we can go forward. Okay. Now going forward. So when you want to charge a capacitor, basically you gotta put it against like a source, like a battery or something, and then it would have.
So could you show me the previous page again?
Yes, please.
Yeah, that thing.
So you'd put it like this. The circuit is made like this, and then okay, like this, and then you have something like that, and there's two-way switch here. So a charging state would be when it is connected to A like this. Okay, and obviously let me just remove this and put a resistor here. Okay, R, the capacitance. So what truly happens is that when it is charging, so we can say when the switch is at A or moved at A, potential difference is experienced due to which electrons move to positive terminal. So what happens is that when the electrons move, there's a this is positive, this is negative. So electrons basically move this way, and when they do, this plate becomes more and more positive. All right. Then the negative side of supply, negative terminal of supply provides electrons to the other plate, which means now electrons from the negative, because there is a potential difference created, they need to fill it up, they start to gather on this side. All right, so this is how charging is taking place. Okay, this way the charges are redistributed. Like for example, the 4 charges that they have left the plate, they basically put back on the other side, so they're redistributed. So 4 go, 4 come back. All right, redistributed by the battery or supply, whatever you put on, to other plate. Now, as more and more charges are redistributed, potential difference across the battery and plates becomes 0, because initially it had some voltage like EMF, and now when the voltage here and the EMF becomes same, so obviously the potential difference is no more. Thus the flow of charge stops. The work done by the battery is stored in the capacitor as energy. Usually this is like 50% of it, but we're going to learn why later on. All right, so you can write this down, please.
Sir, can you explain the third last point again, please?
Third last, as more and more charges are redistributed. Yes, I'll tell you. So to explain the third last point, I'm gonna elaborate it right here. Okay, put it here. So what you guys need to understand is that initially capacitor, when the charges are equal, so the potential difference here is 0 because there's no potential, right? You connect it with the battery, obviously. Connect with the battery. The battery has, let's suppose, 50 volts. So obviously there is a difference in potential, right, Gatika?
Yes, sir.
Between the battery and obviously the capacitor. So what happens is that potential difference between capacitor and battery keeps getting less, right? Now when it keeps getting less, why is that? Because if 4 have left, now electrons are coming on this side, 1 2 3 4. Basically a great repulsive force on the plate for incoming electrons develop, which means obviously the electrons which are coming from here, already it is being filled by other electrons. So now the issue is that these electrons would not let this electron come, or would oppose, because electrons oppose each other, right? They're same charges. Is it clear?
Yes.
And the third thing is that less and less space is left, because the electron density is getting higher and higher, for more charges as charge density increases. Is it clear?
Yes, I got it. Thank you.
Okay. Now, obviously, we need to understand that this whole thing, there are 3 graphs of this as well. So let me just draw these 3 graphs. So first of all, that's not fair. Sometimes it doesn't understand what I want. Okay. So first of all, we're gonna make voltage and time graph, and then we are gonna make charge in coulombs and time graph, and then we are gonna make wait, oh, I don't want this, you didn't fix it. Okay, and then I would like to make graph between current and time. So side by side, this is the voltage across capacitor, and this is the charge on one plate, and this is the current in circuit. So the voltage, basically, let me copy this is more important. Draw it again then. Okay, so the voltage basically keeps on increasing till it becomes like causes a halt, because now if no more charges can enter, so that's the maximum voltage it can reach, and now the potential difference between battery and the capacitor is same, so now it won't increase. The charges, number of charges also increases, and then they become to maximum, where now they stop flowing because the capacity is full, but the current initially is more and then slowly it decreases to 0. The reason is that the current, oh my goodness, the reason is that the current is initially, like, there's a lot of space, so the charges flow fast, and then as the space is being filled, the current becomes smaller and smaller until charges can flow no more, and the capacitor is full. All right, is it clear, everyone? Any questions, please? Okay, you can please draw this, and then we're going to move forward. So then what you guys need to understand is that the same thing would happen if we switch the whole thing, like we go to the discharging, right? For discharging, obviously, what happens is that you are the same circuit, but this time this is A and this is B. Now the capacitor is like fully charged, but then it's connected here, okay, and B, like this. So disconnect the battery, but now because the capacitor has voltage, obviously, so capacitor is going to provide the energy through the current that will flow from one of the plates, because now it will go through the resistor and be back to the capacitor's other plate, and this way it is going to supply the this, right? Now what you guys need to understand is that discharging, within the discharging, you have an exponential decay. The exponential decay has a general formula that applies to all of them, which is x equals to x naught e minus t over rc, that we're gonna discuss more in a bit. Okay. Now, so I'm gonna paste the graphs that we put earlier, which means all of them, because as the voltage, we're looking at voltage across plates. So as the capacitor is discharging, the voltage across plates now go to decrease like this, and the charge on one plate, whatever you're looking at with reference, that also decreases, and the current initially is very high because the potential is higher, but slowly current is 0 because you have given energy. So all of them decreases exponentially. So which means is that for each one of them we can write the same formula. So for example, if I want to check this equation, the highest value is V naught, and then this value is Q naught, this is I naught, and if you want to check voltage at any point with respect to time, you can check. Similarly, you can check Q with respect to time at any point, and I with respect to time at any point. So that means that the decay equation will be V equals to V naught E minus T over RC. This will be Q equals to Q naught E minus T over RC, and this will be I equals to I naught E minus T over RC. This will be used everywhere. Alright, so I'm going to write the things there, like V is the voltage at time t. V naught is the maximum, you can also say peak voltage. T is the time that is elapsed, and R is the resistance, R that was in the circuit, and C is the capacitance. Rest of the things, they also have the same things. You just need to remember that. Okay. Let me know if you have a question. Everyone. Aman, Gatika, Munib, Nadia, Fahar, Joeria, Rafi.
Yes, sir.
Moksha. Okay. Everybody understand this? Very good.
I don't have any doubts.
Okay, perfect. You can write this down, please. And then we're gonna go forward. I just need to get me some water. I'll be back. Okay. Now, so going forward, so the next thing we're going to do is basically, yeah. So time constant, and so discharging, obviously this value that you see right now in the question, that's RC, we should remember that that's equal to
So
time
R
constant.
is resistance, right?
Sorry?
R is resistance, right?
Yes, yes. The resistance in the circuit. So the time taken for a capacitor to discharge to 37% of its maximum value is time constant. Time constant is given by T, and it is the product of resistance and the capacitance. Okay, you guys need to remember this. Now, there is a word that I've written that it's 37%, so it has a meaning. So we'll check it out now. So for this, we're going to derive it a bit. We're going to say, let T be the time taken for capacitor to discharge equal to time constant. Okay, we know that time constant is equal to RC, so we're going to call that T. Now you can use any equation that you want. So I'm using V is equal to V naught E minus T over RC. V here is basically you're going to take a ratio like this, and I'm left with minus T over RC, and RC is basically, I've just said it is T, the time. Obviously this T and that T will cancel out, so it will be E minus 1. If you use the calculator to find what is E minus 1, you'll find it to be 0.37, which means that the voltage will be 0.37 times V naught, which means it is 37% of V naught. It means this is the time taken to discharge the capacitor to 37% of V naught. That is why we call this that. Alright, is it clear, everyone? Let me know if you have a question. Alright, now going forward, talking about the energy stored then. Okay, so one by one we're gonna learn this, and then let's do this. So energy stored in a capacitor, when you draw charge and voltage graph, so it is basically the area under the graph. Okay, so this is the area under the graph. So we say that, because you guys should understand that this is like charge is equal to CV. So Q is equal to CV, that is the equation for capacitance. Right now we see a line which is equivalent to Y equals to mx. So on the y-axis you have Q, on the x-axis you have voltage. So the gradient of this graph will give you the capacitance C. So the greater the gradient means the greater the capacitance of that capacitor is going to be. Okay. Now we also know that V is basically work done per unit charge. So work done is voltage times charge. Right now, because if you see, if we find the area under the graph, it is going to be half times V times Q, and you see this is work done, so that means this is the amount of energy stored, which is half times Q times V. If you notice, there's a half here and there's no half here, so this is the work done by battery, and this is the energy stored in capacitor. So this means that only 50% of energy is stored in the capacitor of the work done by the battery. So not everything is stored. The rest 50% just wasted, unfortunately, in doing, work against the repulsive forces. Is it clear, everyone? Now you can modify this formula, and obviously this could be written as number 1 half times Q times V, because C is equal to Q over V. You can put it like, you can put Q is equal to CV, and then you're gonna get half CV square. You can also get half Q square over C. So all these formulas can be used in different questions, but the main formula that I want you guys to remember is this one, and this is the most recurring formula that they're gonna use. All right. Now, for example, in this question it says define capacitance. So capacitance, you guys already know that it is the ratio of basically the charge on one of the plates to the potential difference across the plates. So you got to do this on your own, so please fill it up. But now we're gonna do this one. The most important question is, and this is a 4-mark question, this would basically be asked again and again and again, and they say explain why capacitor is said to store energy but not charge. Okay, now how do we write this in 4 marks? So we say, number 1, work done by the battery that makes negatives, in fact, let's not be lazy, negative charges move to one of the plates. Okay, then okay, then due to the repulsion, the plate removes one charge from it, then hence a redistribution takes place. So net, this word is the keyword, net charge remains same, only the energy is stored. So this is how you're going to write it for 4 marks. Okay, if you got any questions, please let me know. Juberia, Fahar, Gatika, and Munib, Nadia, Aman, everything is clear? Okay.
So can you explain the second part?
What I'm saying is, so when the electrons basically come here, right? Do you understand? So they kick out the electrons from the other plate. So if the 4 come, 4 electrons are being kicked. So basically what happens is the number of charges on the plate still remain 8. Do you get my point? So as a new charge enters, one leaves. So if you count the number of charges, the net charge remains the same, which means that basically it is the redistribution is taking place and it has nothing to do with storing the charge. It is not storing the charge. Understood?
Yeah, so I was talking about the second one, the one above that.
Due to the repulsion plate, this is what I'm saying. If there are like so many negative charges here and there are also negative charges here, these negatives will kick out these negatives because of repulsion, no?
Yeah.
That's what I mean. Is it clear?
Okay.
Alright. Now, so then this question, you guys are gonna do. This is the same, so this is the homework. Also homework. But this question I'm going to do. So in this question it says the capacitor is charged so that the potential difference between its plate is V0. So the maximum potential is V0. Okay. Then it says The capacitor is then connected across a resistor for a short time and then disconnected. The energy stored in the capacitor is reduced to 1/16th of its value, determines in terms of V naught the potential difference across the capacitor. Okay, so we got to understand this a bit. First of all, we're going to look at the initial energy. The initial energy would be half C V naught square. You guys agree? Let's call this equal to E. Now, the new energy or final one is 1/16th of E, right? So 1/16th of E means that I can write it as E value is half C V naught square. You guys agree? Now, so that would mean that this is going to be 1/32. I think 16 is this one, right? You guys agree or not? Here.
Yes.
Yeah. Okay. So that's basically the new energy. The final one is this one. Okay. Now we gotta basically use we need to find potential difference. We don't need energy, right? So I don't think this is the right approach to do it. Let me just change it a bit. So I'm going to write the first equation right here. E equals to half CV naught square. So I'm going to multiply 2 on this side and C on this side and take under root. So this is V naught, right? Now, and when I'm finding the other energy, the new energy, so that's right, N, this is going to be 1/16th of E, which is equivalent to half the new voltage square. You guys agree? Now what I'm going to do is I'm going to multiply 2 there. So if I multiply 2, this is going to be 2E divided by 16 and C and under root will give me V, right? So if you notice that this part is the same as this part. You guys agree? Essentially, right? Or we can just write it this way. This is much easier. So if I do it this way, and you might see this whole thing is equivalent to this part. So can I say V naught square over 16 is V? Then I can take under root. This will be V equals to V naught over 4. So that would be my answer, which is 0.25 V naught. Is it clear?
Sir, I don't get it.
Okay. I'll do it again. This is a tough question, that's fine. Okay. So, energy is given by half CV square, right? Gatika?
Yes, sir.
If I write for the initial energy, E, I can say it is half CV naught square. You agree?
Yes.
Then the final energy, that's right, N, is given by half CV square because the voltage would be different, right? Smaller one. Understood?
Yes, sir.
Now it says that the new energy is 1/16th of the old one, right? So if I replace this value right here, would you mind?
No.
Okay. So if I replace this, this is going to be 1/16th E equals to half CV square. You get it? Alright.
Yes.
Can I replace this part here?
Okay.
If I do that, then what do you get? 1/16 times half CV naught square equals to half CV square. That's a different method I'm using now. Okay. Now, half cancels with half, C cancels with C. What are you left with? You're left with V naught square over 16 equals to V square. You get it?
Yes, sir.
Now, to find V, we got to take under root on both sides. So this will be V naught over 4, because under root 16 is 4, which is 0.25 V naught. Understood?
Yeah.
Yeah. This is a bit of bit tricky question, but obviously, I hope you guys understand this, right? Now, should I go forward now? Please have a look. If you still don't understand, let me know. I can do another method. No worries. Okay. Ooh, wow. You guys are tough. Okay, let me do it here then. Okay, so what I'm doing is, I know that energy is given by half CV naught square, and 1/16th of energy is half CV square, right? Do you understand this?
Yes, sir.
So now you multiply this. You multiply, make V naught the subject. Can I say V naught square would be 2E divided by C then?
Yes.
And can I say on the other side, it will be 2E over C times 1/16 is equal to V naught, V square?
Yes.
This value and this value is the same, no? Can I replace that, please? So if I replace, it's going to be V naught times 1/16 equals to V square. Take under root, you're going to get the same answer.
Okay.
See? So whatever you like, you can do it. Alright, is it clear?
Yes, sir.
Alright, now going to the next part. Oh, okay. Now, this is a very, very interesting question. Basically, this question belongs to I should have put a heading. So you guys should also put heading on your PDF. Right change of energy. Now, why this is important? Because there is a wrong method of doing this, and there is a right method of doing this. So we're going to do both and learn why you would get a wrong answer in case you get this question. So let's do this first. So the wrong method is that when they say find the change in energy, so calculated energy dissipated, that's the change. What most people do is they find the change in voltage 1, which means they do voltage 1 minus voltage. So they do 18 minus 12, so that's going to be 6 volts, right? Is it clear? Then what they do is they put energy equals to half CV square, so half times the capacitance is 4700 times 10 raised to minus 6 micros minus 6 multiplied by 6 whole square. Kartika, can you or anybody please let me find this answer? Let me help. Help, please help.
So 0.085.
0.085 joules. So this is your answer. But actually, this is wrong. Why? So first of all, what you're going to do is, when you find the change in energy, you got to do half C1 square minus half C CV2 whole square. Okay. Now, when you do that, you're doing 4700 times 10 raised to minus 6, and then what was that? 18 whole square minus 12 whole square. Because I took half C and half C common, that's fine. Can you please find? Use the brackets, please, and then find the answer.
0.423.
0.423 joules. Now, this is the correct answer. Why is this? Because if you find the change in this, basically you're using a formula which is half C V1 minus V2 whole square, if you do this method. But then if you use this method, you're doing half C V1 square minus V2 square. If you look at both of them, this part of the equation belongs to a math function of a minus b whole square, which is basically opened up as a square minus 2ab plus b square. And if you notice this one, this is basically a square minus b square function, which is opened as a minus b, a plus b. Both functions are different. So you're not supposed to find the change in voltage, you're supposed to find the change in energy, and that's how you do it. Is it clear? I just wanted to, put it forward because this is the most common mistake. And although it's 3 marks, and if you do the first one, you just lose 3 marks, it's not good, right? Okay. Alright, Mokshit and Munib and Nadia, Aman, Fahar, Katika, Juwaria. Any questions now?
No, sir.
Okay, so I'm going to go forward then. So this question, I kept it because, why is this? Oh no, I did 2 of them together. That's not good. And why is this question here? It should not be here. Chalo, no worries. You can, basically this is the same question, but chalo, never mind. You guys can do this question later as homework, and you can do this later as well. But we're gonna first write some of the uses of capacitors. Now, they're not gonna inquire you with the uses in detail. You just need to give them. Alright, certain uses. I'm going to write some uses, and you can pick any one of them and write it in your exam. It will give you credit. So capacitors are used as a temporary storage of energy. This is also known as buffer circuit. So you can just write one word if you want to. These are used in tuning circuits. These are used in smoothing. This is one thing that we're gonna learn in detail much later in, I think, alternating currents. Smoothing circuit when converting alternating current to direct current. Then it is also used in filter circuits. It is used in surge protection device, and it is used in time delay circuits as well. Okay, so you got to remember that. Now, temporary use.
Blocking DC current also, I think, right?
Blocking DC current. Surge, yeah. Like if there's a large current that flows, you can actually protect something. That's true. Okay. Now, tuning circuits are basically in musical instruments. You gotta, use them to tune something, like auto tune. That is when singers are really bad at singing, but computer can tune their voices. So that's used. That's done by capacitors, and then filter circuits are basically circuits which you can change sort of bass, treble, and stuff like that. And then surge protection is if large current flows suddenly, you can protect your appliances. And time delay is basically, if you might have seen, in like really expensive cars, the lights turn on slowly and go out slowly. That's how you can do it using a capacitor as well. Anyway, I hope you understand this. And yeah, so let's go forward then. So then we got to learn the capacitors when they're put in series. So this is your homework, part A, but I'm gonna do this. So when you put capacitor in series, you guys need to understand that each one will get voltage differently, which means in series you should remember that the charge on each capacitor is same, and it is basically the same charge on the smallest capacitor. So whatever the charge on the smallest capacitor is, that would be the same on everybody else. So charge is same on all of these. Then the total voltage, which is V, is given by the sum of all potential differences that's there. Okay, so we're gonna use this. So since V is equal to V total is equal to V1 plus V2 plus V3, this means that the charge over C total, how do I know this comes? Because C was Q over V, so V will be Q over C, okay, like that, will be equal to Q over C1 plus Q over C2 plus Q over C3. Because charge is same, so we're going to cancel this out. So we're left with C total can be found out when you add the reciprocals of all the capacitances, like this. So this derivation is included, and obviously this will come in your exam as well, like you can see. So it's pretty easy, please don't mess it up. Chalo, how stupid I am. Alright, then we're gonna go and check out this circuit. Okay, so it says a battery of EMF 12 volts. An negligible internal resistance is connected to a network of two resistors, two basic capacitors and the resistor. The capacitors have the capacitance of 200 microfarad and 600 microfarad. The switch has two positions, A and B, as you can see. So the question is that the switch is moved to position A. So when it is moved to position A, right? So it says calculate the combined capacitance of two resistors. Because they are in series right now, they're connected by just one whole circuit. So that means that we have to use the combined resistance of C total equals to 1 upon, what was that, 600 probably, and 1 upon 200, I don't know. 200, 600, yeah. So what will be the C total, please? You don't need to convert into microfarads. Usually they will give you the same thing, so don't worry about that.
150.
150 microfarads. Okay, so that's the answer. Now they say the charge on 600. Now obviously in a series the charge remains the same. So we have the total capacitance, we have the total voltage. So we're going to use C is equal to Q over V. And the charge will be 150 microfarad times 12. What you get? Yes, please.
1.8 times 10 raised to minus 3.
10 raised to minus 3 coulombs, right? You converted them? Okay.
Yes.
So 1.8 10 raised to. So this would be the charge on both of them. Like this one will have the same charge, this one will have the same charge. And then it says the potential difference across 600. So you just need to use Q is equal to CV. Again, this time the charge is the same. The capacitance is 600 times 10 raised to minus 6 and the voltage we need. Okay, can you please find this?
Three point zero.
3.0. So that would be the voltage. Any questions, please let me know if you do not understand something.
And second part, we need to convert the capacitance, right?
Yeah, obviously we need to convert it because this is in coulombs, so that's why. Now this question is very interesting, and this is fairly, I think it's 16. Okay, the switch is now moved from position A to position B. If the switch is moved from position A to position B, right here, so according to this question, then this initially the initial voltage here was 3.0 volts, and this is the resistor R, and the charge that was basically in it was 1.8 times 10 raised to minus 3 coulombs. Okay, so we're going to keep this in mind. And now it says calculate the potential difference across 6 capacitor when it has discharged to 50% of its initial value. Oh, okay. Do we have the resistance? Let me check first. Oh no, that's not fair. Okay, so no worries. So this is a very similar question to the previous one. So suppose that initial energy was E, right? The new energy is half E because it has gone 50% down. Do you guys agree? So if I say it is half C V naught square and this is half C V square, you guys would mind? No, right? So can I put this E here? So I'm going to get half into half C V naught square equals to half C V square. This half C and C will cancel out. So V naught square over 2 is equal to V square. You're going to take under root. So V will be equal to V naught over under root 2. What was V naught initially? 3 divided by under root 2. What you get? This is the same question as the one we've just done, 1 over 116. Yes.
2.1.
2.1 volts. Okay, everybody understands this? Please let me know if you do not understand this. That's good. That's it. Okay, so I'm then gonna go to the next part where you need to prove whether, okay, so like this question, it says state two functions of capacitors connected in electrical circuits. So this is your homework. You just need to put the 6 things I've told you. Yeah. So if they ask you this, you can say it is buffer circuit, tuning circuit, surge protection, whatever you want to write, right?
So how did you get 3?
How did I get 3?
Yeah.
From the previous part.
Oh, okay.
Yeah. Okay, do you understand now? Okay. So now in this you can put any two functions that we've studied, but we're gonna move to this one. So then it says explain why the charge on positive plate of each capacitor is different, because in parallel we need to understand that the voltage remains same, right? So charge is different on each capacitor. So this is the thing about this. So in this one, if this is the voltage, this one gets the voltage, this one gets the same, but the charge on each one of these are different. So the total charge can be given by Q1 plus Q2 plus Q3. This is the first step you want to take, okay? Now, then because Q is equal to CV, which means C total will be equal to times V equals to C1V plus C2V plus C3V. V cancels out, so you get C total equals to C1 plus C2 plus C3, and that's what you need to do. All right, for 2 marks it's a very simple derivation. So you guys need to remember, in series the charge remains the same, in parallel the voltage remains the same on each branch, so that's fine. Is it clear, everyone? Okay, now okay, I was thinking maybe we could have just done finish this, but I don't think so we will be able to, but never mind, let's do this. So first of all, it says find the total capacitance between 2 points. So whenever you see some circuit like this, so always first try to do the inner circuit and then follow through the second circuit. Okay, this is the main idea behind this. So first circuit is basically a parallel circuit. So in parallel, the total capacitance is just added up. So 48 plus 48. So it's going to be, what is 48 and 48? I don't know. 96? Okay, 96 microfarad. And then this hole has 96 microfarad, which is now in series with this, which means that we are going to do 1 upon C total equals to 1 upon 96 plus 1 upon 48. So what you get, please? 32 microfarads. Now it says the maximum safe potential working that can be applied to one of the circuit. Okay, I'm gonna come back to this in a bit, okay? But no worries. First you write this and then we're gonna go forward. And then I think I will give you this as homework, and then you can do it when I've taught you this one. Anyway, so going to this one, this is just your homework as well. You can obviously do this now. Always do the first inner one and then the outer one, please. Then going to this one, this is also your homework, pretty easy question. And now we're going to go to safe working. Again, 2 functions, you already know, you can do it. Now, when something is written like this, like 3 capacitors each marked with this, what does that mean? It means that if you connect them beyond 6 volts, capacitor will blow. So you got to make sure that each one gets at most 6, but they can get less voltage, but not more than this. Should not exceed from this value. All right, should not exceed. Now there's 2 ways that we can handle this one. So let me just try and do it right now so you guys understand this. First of all, they're gonna say each one is 30, so you got to find the total one. So here this will be 30, this will be 30. So in parallel you just add them up. It means total is 60 and this is 30. So we can find the total using 1 upon 30 plus 1 upon 60. And the C total is going to be What do you guys say?
20.
20. Okay, 20 microfarad. Now it says the maximum potential that can be safely applied between this. Now what you do? When you have the total capacitance, you simply basically apply the maximum to, I'm just saying, apply max voltage to the minimum capacitance. All right. So I'm gonna basically, what I'm gonna do is I'm gonna say this is my combination 1 and this is my combination 2. Okay, this one. Okay. So right now, if you see, combination 2 has a capacitance of 60 microfarad and combination 1 is 30. So what I'm going to do is I'm going to apply the maximum voltage that can be applied here. Okay. And when I do that, then I'm going to use Q equals to CV to find the charge on it. So the charge is going to be 30 microfarads times 6, and that would be 180 microcoulombs. Is it clear, everyone? Now this would mean that this combination gets 180 microcoulomb and this whole combination also has 180 microcoulomb, like the whole one will get it. All right, then what I'm going to do is in the third step I'm going to use Q equals to CV. I have the maximum capacitance as this, the maximum applied is this. Capacitance there was 60 and I can find the voltage. Yes, please. Micro and micro will cancel out. So 60 over 180, that's 3, right? So it means that I can apply 3 volts here, 3 volts here, and 6 volts here. That's how it will work. So now, sorry, this is not the answer. So if this whole section, which is parallel, gets 3, this gets 9. So total is 6 plus 3. So the maximum voltage that I can apply in this circuit is 9 volts. Please have a look and let me know if you have a question. Okay. Now this is like one way of doing this. So this is pretty easy. So you basically find the total capacitance, then you find basically the minimum capacitance, whichever that is in the circuit, you apply the maximum voltage there, and then what you do is you find the charge on that. Whatever the charge on that is, that will be the same on the other combination, and then use that charge to find the voltage by using the total capacitance there. Is it clear? Any questions now? Now, there is an alternate method to this as well. The alternate method is, I'm going to show you this. And if you like that method, you can do it, but it's not necessary. So you got 30 here, you got 30 here, farads, and you got 30 here. And total, is 60 microfarad because they're in parallel. So you can make a ratio. You can say the combination 1 ratio combination 2 is 30 ratio 60. So you get 1 ratio 2. Do you guys understand this? Now if you notice, the formula is Q equals to CV. We can write it this way. So C and V are inversely proportional. So that means that when you write voltage in first section, voltage in second section, what you got to do is you have to take the maximum value here, write both here, and divide by ratios. Like it had 1, so you divide by 1. It had 2, so divide by 2. So your ratio becomes 2 ratio 1. Now, so V1 ratio V2 becomes 2 ratio 1. So the first combination you apply 6 volts and you find what will be the other one. Cross multiply, please. So it's going to be 2x equals to 6. So x will be 3 volts, which means in this combination you have applied 3 volts, and in this combination you have 6 volts. So the total is going to be 6 plus 3, that's 9. So whether you like the ratio method or the one that involves equations, that's up to you. It will give you the same answer. Okay. Please have a look and let me know if you have a question. Now, the question that I left and gave you as a homework, that is just a practice question behind. You can do it. And if you don't understand that, do let me know. I can help you with that in the next class. Okay. Finally, we have this part where we need to design circuits as well. So you have this one as homework, but I'm going to do. So for example, it says a student has 3 capacitors. 2 capacitors have the capacitance of this and one has this. So draw a label diagram in which case to use 3 capacitors to give total is this. So we got 2 capacitors of 4 and we got 1 capacitor as 8. Now I got to think that how would I reduce this, right? So first of all, I need to understand this. I need to realize that basically in series, when I connect things in series, that reduces the capacitances, right? So if I do that, let's try. This is a bit of hit and trial. So you can use a pencil to do this, and then later on you can, draw this later on. It doesn't really matter. So if I do the total 1 upon 4 plus 1 upon 4 plus 1 upon 8, what do you get there for C total? I think you should be getting 1.6 though. I don't know.
Yeah, it's 1.6.
Right, 1.6. Because I understand that basically because in series the overall capacitance reduces. The reason is that I have to take reciprocals, right? But then in the next question says you have to put them such a way that it gives you 10. Okay. So how does it give me 10? So if I have 4 and 4 and I have 8. So I know if I put 8 like this, so 8 will be added to 2. So I need these two I can combine to make 2, which means, and then if I put 8 in parallel to them and these two in series, so then it's basically going to give me, like in series, it would be 1 upon 4 plus 1 upon 4 in this section only I'm talking about. So that is going to give me 2 over 4, which is basically 2, right? So overall, these two, in this line, there will be 2 microfarad. And because these two are parallel with this, so in parallel, we just simply add them. So 2 plus 8 gives me 10. So that's how you will do it. Is it clear? Let me know if you have a question. So remember, capacitance is reduced in series, capacitance is increased in parallel. So you got to remember that. So if you want to get a bigger value, you put things in parallel. If you want to get a smaller value, you put them in series, and that will help you design these circuits like that. Okay. I don't think so. Yeah. Okay. Javeria, Mokshit, Munib, Nadia, Fahar, Aman, everything is clear?
Yes, sir.
Yes, sir.
Okay, pretty good. So then, this one obviously you need to design. So that's going to be your homework to practice it a bit, and I believe you guys will be able to do it. Now, although I wanted to finish this, but chalo, let's see if we can do it in like this. So we're looking at now the half-life of the capacitance. Oh my goodness. Wait. Okay. So half-life means what is the time taken for a capacitor to basically go like become half of the original value. So that's going to be V naught, and we're looking at a V naught by 2. And we want the time of half-life, which means we want a value of V at which V naught will be exactly half, and every time it will be the same. So we just need to derive this a bit, and that's pretty simple to do. What you need to understand is that we're saying that at time equals to time of half-life, V naught will be divided by 2, right? So we're going to use any equation like V is equal to V naught E minus T over RC. This V will be V naught by 2, that is V naught E minus, this will be T of half-life, and that's RC. So this will cancel out, so this is going to be half E minus T half over RC. This is a symbol, it's not like we're not halving it off, it's just a symbol. So then what you're going to do is you're gonna take ln here, because ln removes E. So if I take ln here, so it's going to be ln half, and the rest of the things will come out, times ln E. ln E is just 1 equal to 1. So then you're gonna get, if you move 2 up, then it will be minus ln 2 multiplied by RC equals to minus half time of half-life. So you cancel this out. So time of half-life can be found out by ln 2 multiplied by RC, and that's how you can find that how much time will it take to become half of it every single time. Okay, is it clear? All right. So some of the questions, some of things are quite new, because unfortunately we do not have we do not have more recent questions, as few things I've just added now. So I'll give you a practice worksheet later on as well, don't worry. Like, write this down, let me know if you do not understand this small derivation. Okay, fair enough. So I'm gonna go to the next part then, where
I'm sorry, I haven't done my thing.
yeah, okay, sorry. All right then. Should I go forward now? Okay.
Done, sir.
Okay, very nice. So, for example, okay, this is just basically a question from routine. So this will be your homework. That's basically the simple question. But we'd like to go on this one. Okay. Now, in a hollow sphere or a charged sphere, you just need to remember that this will be your question. Sorry, this part only. The rest of this I'm gonna do. So they will say show that the capacitance of a hollow sphere or something like that, a metal sphere like this one, has this value. So this is a derivation we need to learn. So first of all, we're going to use the first equation. We're going to say Q is equal to CV, and then we also know that V is equal to KQ over R because of the electric field that we know, right? So I'm going to put this V right into this, and if I do that, it's going to be Q equals to C times KQ over R. Q and Q will cancel out, V will go there, so it will be basically V. Oh, we need to find C. Wait a second, why is this V? This is R, sorry. So it's gonna be R over K equals to C. Alright, so we get here. Now this is our equation. Since K itself is 1 upon 4 pi epsilon, so we can put that, and then you guys know that's going to be R over 1 upon 4 pi epsilon. You can multiply it here. So C is going to be 4 pi epsilon R, and that is basically what you need to remember. Now here I just want to give you a note, and the note is that in this sphere, capacitance is directly proportional to the radius of the sphere. So the larger the radius is going to be, the greater the capacitance is going to be, and that's what you guys need to think, okay, when doing this question. Anyway, so keeping that in mind, then they say the radius is this, and for this just use the value. Well, it's up to you if you want to use epsilon, but I like this formula more because it's easier. So it's up to you if you want to use it. But we want to find the capacitance. R value is 0.36. You got to change it into meters because K is also in SI units. So 8.99 times 10 raised to minus 11. 9. Okay. So can you please find the capacitance? Epsilon value is given, it's 8.85 times 10 raised to minus 12. If you want to use it, you can use it too. So if you like, you can use 4 pi 8.85 times 10 raised to minus 12 and multiplied by 0.36. That would give you the same answer. Yes, anybody please find this?
4 times 10 raised to negative 11.
4.0 times 10 raised to negative 11. Then it says the charge required to raise the potential from 0 to this. Alright, so we got to find the charge required to raise the potential. So that's pretty simple. Q is equal to CV. We have the capacitance, right? And we got to find the potential. So 4.0 times 10 raised to minus 11 times 7.0 times 10 raised to 5. What you get? So this part of this chapter is so easy. You can always, do it whenever you want to. It's pretty simple that way. Okay, yes, please go on.
2.8 times 10 raised to negative 5.
Negative 5 coulombs, that would be the charge. All right, so let me know if you guys missed out anything or anything that I went too fast with that I can explain again. Okay, we have 4 minutes left, and thank God we finished this, and thank God you guys stayed for 1 hour 30 minutes, but that's fine. Okay, this way we can actually finish each chapter. I don't think we have much course left. How much course is left? 1 2 3 4 5 6 7 8 9 chapters. I think 9.
So 6.
How? Magnetism, electromagnetism, alternating current, quantum, nuclear, X-rays, ultrasound, PET.
See, I'm counting this separate. I was counting it as medical physics.
Oh, medical. Okay, then 6. Okay. Okay, fine. So the next one.
Nuclear physics.
Yeah. So if we do it with the same, vigor, we're gonna finish this by, I think, in 9 more classes, which is great. All right. So rest of
the
the.
same part for the previous question.
Yeah.
So what about
Sorry, come again. After this.
Yeah, this one, C part.
Okay. It says in order to investigate electrical discharge lightning in a laboratory, an isolated metal sphere of radius is charged to a potential this. At this potential, there is an electrical discharge which causes the sphere to lose 75% of its energy. And calculate the capacitance sphere stating its unit. So yeah, it's alright. So Gatika, in this one, you need energy is equal to half CV squared. Okay, so again, this basically has the same effect. What you're going to do is you have the radius, you have the potential, right? So the capacitance phase starting the unit in which it is stating the unit in which it is measured. Wait a second. Why? We have the radius and charge potential. At this potential, there is an electrical discharge which sphere loses 75% of energy. So if it is losing this energy, you got to find the voltage first. Okay, so we're going to use this the same point. 75% of energy means that now only, like, it will be 0.75. What do you say? 0.25, right? And we need to find v square. Is it clear? Now you just put it this way: 0.25 times half cv naught square equals to half cv square. This cancels out, and Ratika, you're gonna get 1.2 times 10 raised to the power 6 divided by under root of 0.25. What you get then?
2.4 times 10 raised to 6.
That's not fair. Why is it higher then? It should be lower, no?
I don't know.
Yeah, it should be lower. There's some mistake in this. Wait, I made a mistake here. So I'm saying that basically, initially, this is the amount of voltage, and we've got to find the voltage, new voltage. That's what I want. It says the energy that it had. At this, there is an electrical discharge which the sphere loses 75% of its energy. So that I'm just using the same thing. Okay, so yeah, and but it says stating the capacitance. Why would you want capacitance when you have the formula above? You have the calculate the capacitance phase stating the units which is measured. Eh? But I don't think why they have to do this to us. It's okay. All right, so energy, it goes like 25% of it is remaining right now that I can see. That means that it's going to be energy, and then energy 1 is E, so it means 0.25 of E. So let's just write that, and let's see. E equals to half CV naught square, and E1, let's write, this is the E1, the new energy is going to be 0.25 of E, right? So then
Sir, I think you find
Nani, this is the
and then
same.
just make it
Yeah,
0.25
yeah,
with the
yeah.
voltage.
I'm doing the same thing. I'm trying to do that. So C, we can find it through the value, like it's C times, and then we can write 1.2 times 10 raised to the 6 whole square. Okay, and this needs to be equal to this one, because if we put this right here, so the new energy is going to be 0.25. There was some mistake, I did the same way. 1.2 times 10 raised to the 6 whole square. Yes, so this is what we need, and the issue is that this new energy is this much. Yes, which is, it should be 0.25 for some reason, and yeah, there has to be, it's new E, and that's equals to half CV square. Okay, fair enough. Yes, so now C and C should cancel out like we have done before. Half and half cancels out, so V square is equal to 0.25 times 1.2 times 10 raised to the 6 whole square, and we're gonna take the root. Somehow I got it under that, which was wrong. Okay, can you please find this? What you get?
6 times 10 raised to power 5.
6 times 10 raised to power 5 volts. Okay, 5, fair enough. And then you can just use, but this is what we just need capacitance for 3 marks. Why have they given capacitance for 3 mark when we have the resistance? Okay, wait, Kartika, can you also do 8.85 times 10 raised to minus 11? That makes me very sad. Can you do this, please? What you get? Just cancel out. Why would they ask for 3 marks?
That is 45365.
What? Sorry, minus 12. Okay, yes,
So
please.
5.05.
Sorry, that's minus 12.
What? No, I'm talking about C.
7 times 10 raised to negative 11.
7 times 10 is to minus 11.
Wait, how?
Okay. Hello. हेलो जी सर अस्सलाम वालेकुम यस यस जी जी हाँ वो उसको वेट ही कर रहा हूँ मैं इसका सो इशी जी 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 और okay so I don't think so why they've given 3 marks but we can just find directly this I don't know Gatika why 3 marks 3 marks
So it's minus 12, so no minus 11.
yeah it's minus 12 I wrote minus 12 again here hello क्लास के बाद wait okay yes I don't know Gatika why it's 3 marks but it has to be this answer anyway can you please check
So we don't have to do all this working?
no I don't think so I have no idea I thought this was like required some working that's why I did it so much but it's not they've just given 3 marks for free that's not fair all right so I believe that would be all you guys can continue with your chemistry class and